Alrighty. So 24.5 is on the Doppler effect and how it applies to electromagnetic waves. Now the Doppler effect is something that previously is covered in our textbook, though you may not have gotten to it in your last class, and it applies to sound. That's what we most commonly observe, as in the comic with Sheldon here from the Big Bang Theory, where it says, I don't care if anyone gets it, I'm going as the Doppler effect. If I have to, I can demonstrate. Meow. And that's a great demonstration, nerdy though it may be. If you hear a car or a fire engine driving by with their siren blaring, you'll hear that the pitch changes. The notes that you hear, the frequency, is another way of saying it, right? Where it goes higher as it gets closer, and then as it goes away, it goes to a lower pitch or a lower frequency. So that's what I want you to hold in mind. Here we aren't going to be looking at with sound. We'll be actually looking at it with light. So like sound, electromagnetic waves or light can also exhibit this Doppler effect, but it's going to be different for two reasons. One, sound waves require a medium, whereas electromagnetic waves do not. So light can travel through outer space, which is a vacuum. For sound, we also only care about the motion relative to the medium that's important, but for light, you only need the relative motion. So it's actually a lot simpler when we're considering light as opposed to sound. And so our equation for electromagnetic waves is that the observed frequency, f sub 0, is equal, or f sub O, is equal to the frequency of the source, f sub S, times the quantity 1 plus or minus v rel, the relative speed between the source of the light and the observer, and then c, the speed of light. And this will apply as long as that relative speed is much, much less than the speed of light, which is going to be true in our everyday cases. If you start traveling really, really fast, you're going to need a more complicated equation than this. Now, this plus or minus here is an important detail, and that's one where you'll have to fill it in based upon the description in the problem. So we put a positive sign if the source and the observer are coming together. If the source is moving towards the observer or the observer is moving towards the source, either way, if they're coming towards each other to positive, we'll use a minus if they're moving apart. If the distance between them is increasing, either way there. And that fits with our rough picture that we have with sound, right? That if they're moving towards each other as the siren's approaching, the pitch or the frequency increases, and so that's the positive to make it a higher observed frequency. And as they're moving apart, that takes away from the frequency that's going to be observed, and so it's a lower frequency. So there you have it. That's our key equation for this section. So let's look at an example here that's a realistic example, but then I simplified it to be a little less realistic to real life, but closer to what you'll have to solve. So radar guns and speed traps. The radar gun of a police car emits an electromagnetic wave with a frequency of 8.0 times 10 to the 9 hertz. The approach is essentially head-on. The wave from the gun reflects from the speeding car and returns to the police car, where onboard equipment measures its frequency to be greater than the emitted wave by 2,100 hertz. Find the speed of the car with respect to the highway. The police car is parked. So the addition I made here to make it simpler and more like what you'd see on the homework is the speeding car detects the police car's radar gun at a frequency of 1,040 hertz above 8 times 10 to the 9 hertz. So there's a lot of clues there. And let's see if we can figure out what we know in this. I'm going to stop sharing that so that we can work on a whiteboard and trying this out for the first time. Right, so we have the speeding car that is in red. And then the police car that it mentions is parked. So that one's not moving. And they also said it's approximately head-on. So because we know that that is stationary, we can write v equals 0 there, which is great. And then we can jot down the other pieces of information that they give us, right? They give us this 8 times 10 to the 9 hertz. Then they give us what the police car detects, and as well as what the speeding car detects, which I'm going to focus on that. So the 8.0 is the source. Speeding car detects this 1040 hertz above. So 1040 plus 8 times 10 to the 9 hertz. So what we're going to just note here is that the source is going to be our f sub s, and what the speeding car detects is going to be our f sub o. That is our observer here with the modified problem. And we want to know how fast the car is going with respect to the highway or with respect to the police car, which means we're solving for the relative speed. Right? And so if we go back to our full equation, the full equation has that f sub o is equal to fs times 1, and then plus or minus this v rel divided by c. And remember, we have to decide if it's a plus or a minus, so think for a moment which one it is for this scenario. Well, since they're moving towards each other, it is going to be a plus. So if you thought that, you are in good shape. So we'll keep the plus, lose the minus there, and now we're just solving for, oops, sorry, I got off there. Now we just need to rearrange this to solve for v rel, because we know FO, we know FS, and we know C. So I'm going to start by distributing out this FS so that we don't have to have two terms there. So FO is equal to FS times 1 plus, I'm dropping the minus, FS times v rel over C. Right, so now I want to get v rel by itself, so I'm going to subtract the first FS across. So FO minus FS is equal to FS v rel over C. And now we can just divide both sides by FS and multiply by C, and we are home free. I'm going to do both steps at once if you don't mind. Dividing by FS, multiplying both sides by C. And so then the FS's cancel, the C's cancel, and we're left with this expression for v rel. And I'm still on the board, so I think we're okay. Sorry for the glare there. So v rel is equal to FO minus FS times C divided by FS. That's the full simple equation. One cool thing to note, FO minus FS, the difference between these is just going to be 1040. So we can save ourselves some work by just plugging in 1040 hertz. So as I'm coming over here, I'll put in 1040 hertz because it's 1040 hertz above the source, and we're taking the difference from the source, so that works out. Divide by 8 times 10 to the 9 hertz, and then times the speed of light. 3 times 10 to the 8 meters per second. All right. And so then if you calculate that out, being careful, you know, the 10 to the 8, the 10 to the 9 will mostly cancel out there. So we're left with something that's not crazy large. It's just 39 with the units of the speed of light, meters per second. And this is also on the last slides, so you're welcome to check it out there in order to see that. I also included the more complicated way of solving it, but you do not need to worry about that. So as long as you understand this process, then you are totally good. So that is the Doppler effect for electromagnetic waves.